p is 0.
Oh.
When as p goes to 0 or 1. It's one of the nice properties of it.
Oh.
Yeah. Cool. Happy to answer more questions as we go. We'll get started. I will just remind you that homework is not done due this week, but next week. If you haven't started, I highly recommend you start. It is not going to be like a 1-hour assignment. It's not even going to be a 2-hour assignment. It's probably not even going to be a 5-hour assignment. So start soon. Yeah.
So I'd like to know regarding the gradient descent, is it an analytical method or like numerical, and what is the main difference between the numerical and the analytical approach?
For computing gradients?
Yes.
The analytical approach is to just, like write down what the derivative is. We know what it is. Like we have a whole table of these things. Like we know what it is. If I take a derivative of e to the x, I have e to the x. If I take a derivative like log of x, I have 1 over x. And I literally just like replace those derivatives with those functions, right? Numerical is just you use the definition. You don't appeal to a different function. You use the definition of derivative and just pick a small, whatever h, right? It's like f of x plus h minus x over h. And you pick a small h and you use that as an approximation to the actual derivative. So in the one case you have access to the actual formula for the derivative, and the other you just approximate it. That's the difference.
So when we are doing gradient descent, essentially we are doing a numerical approach.
No, we do. There's kind of an in between, which is automatic differentiation, which is like kind of the best of both worlds, where you do look things up, but you use like numerical approximations where appropriate. And yeah, so what we talk about today, backpropagation, like backpropagation works because there's, like in practice it works because there's just such nice libraries out there for doing things like automatic differentiation. Like there's just really, they've existed in different forms for a while now, but like in the modern frameworks like PyTorch, like TensorFlow, like JAX in particular, is all about like how to automatically differentiate the functions you use. And JAX in particular is interesting because it actually it makes differentiation kind of first class operation, and you can differentiate a lot of things, not just like mathematical formula, but you can differentiate for loops. You can differentiate basically most operations that you can write down, you can actually differentiate through, even if that really isn't a good idea, you can still do it. It's pretty cool. And then there's of course there's languages specifically for this, but JAX is kind of a nice. JAX is like an extension of what you find like in PyTorch, for instance, and it applies for NumPy arrays, which is really cool. It applies directly to them. Anyways, yeah, good questions. All right. Let's get started. So far, what have we done? We've really focused on kind of simple building blocks. So we have score functions; they've been linear functions, right? So this is giving scores for each of the classes. So if you have 10 classes, W is a matrix with 10 rows. If it's got 100 classes, it's a matrix of 100 rows. Each one of those rows being some kind of prototypical example of the thing in the class. Anyways, you get this score per class, and then what do you do with those scores? Well, you need to compute some. You need to have some way of quantifying how well you're doing at this task, and in classification, you want to have some way of saying, like, are we getting the class, right or not? So we talked about a couple different losses. This like SBM loss or hinge loss. And we talked about softmax loss. We talked about cross entropy loss. This is using softmax to represent the outputs as a probability distribution, and then computing the negative log likelihood of the correct class. And that's what. So this is your cross entropy loss. This is our hinge loss. We use that as per data point, and of course we talked about computing getting some sort of notion of the loss over the entire data set. We often do that as like the average loss over all the points in your data set. We talked about, we often will add a regularization term that specifies like something that we prefer about the way that the weights look. And if you've done some kind of statistical learning theory, what you would have is something like, this is like an estimator for a statistic that we care about. Often you can think of it as like an unbiased estimator. This term will actually bias that estimator, meaning like we no longer have, like in the limit of large data, an estimator that gives us like the expected value of the estimator. But the trade-off is we have a little bit of bias, but we reduce often like variance quite a bit. And there's in machine learning, you probably have heard, if you spend any time in machine learning, you probably heard of like the bias variance trade-off, where you're trying to estimate parameters using things like these loss functions. And this is one of the times where this comes in. We often trade off a little bit of bias, and it could be a lot of bias depending on depending on what this term is or what the value of this weight lambda is. But often what it's doing is it's reducing the variance in like the estimates being made. So if these weights are, the prototypical example is if these weights are quite large, then we don't generalize well to like test examples. So what that means is that we get like a lot of variance in the predictions being made. But if we sort of make those weights smaller, then actually we get kind of a smoother function in the end, a smoother loss. And it's like fitting the parameters end up fitting, like they end up generalizing better to examples of results. So we get a bias estimator, but we have less variance. And this is like what regularization. I think another definition of regularization is really like that. It's anything that we do to the loss function that basically keeps training error the same, but is meant to reduce the gap between training and test error. Okay, so then we talked about loss surfaces. Like what we're trying to do is find like the minimum or a good minimum in these losses, but they're extremely non-convex functions, meaning that they have lots and lots and lots of local minima. So like, what do you usually you should run away from a problem like this, because like there's just no hope in this working well. But for some reason, it's not just like unknown, but there's it's not totally known either. There's a lot of research people do in these kinds of questions. But it turns out like in deep learning very often, the local minima that we find are often like equivalent to each other in some sense, no matter where you start. Not always, but like often. And it turns out that like this tends to work pretty well, actually. And like, what do we do in this case? Well, if we have a loss surface, and we have the capability of computing gradients of that loss, then we can just implement simple first-order optimization schemes like gradient descent to find our way from where we are now into some local minima of that surface. And then we're like, hopefully that's a good set of parameters, right? Stop me if like things I'm saying don't make any sense, because we're kind of like we're going really fast through like many semesters of machine learning optimization, things like that.
So the data loss is non-convex, but isn't the regularization convex? Just big parabola that just.
It could be, yeah. Like when we do like L2, it is a big honking parabola with a zero plot. But you're adding a convex function to some big non-convex.
So when we do
it's not big, but like really non-convex surface, and so you're getting still a non-convex surface.
So when we do the regularization and the theta loss for weights, does that include the bias plus B?
Yeah, yes, exactly. Yeah, like we've been kind of like skipping that a little bit, like we haven't been putting the B in. But yeah, you would apply that to all of your weights and biases.
Or does it really matter? Because the B just moves it up and down. It doesn't.
You're right, but you tend to just apply it to all the weights. Yeah. I should say any parameter. So weights and biases. Anyways, so what's great is we have our loss surface, defined by the data, and our current set of parameters. We can compute a derivative, a gradient essentially of that in however many, like whatever is the dimension, the number of parameters that we have. This is often like huge. Now the bigger companies are training models with hundreds of trillions of parameters, so this is an enormously high-dimensional space, kind of hard to imagine what exactly it is. But no matter, you start someplace in this space, you can compute a gradient, and that gradient is telling you, at least locally, the gradient is actually telling you which direction to go to, locally have like a maximum increase in the loss. But we want to go to, we set up our problem so that we want lower loss. So we just multiply by -1, and now we're looking in the direction of the greatest descent, or greatest loss of the loss. But just reduction of the loss. And we just we have to just kind of have this balance of like not stepping too far, because this gradient really is only giving you information like very local. So like the more curved things are around wherever you are, like the worse an approximation that becomes as you step further away, right? You can just kind of picture this in like this kind of 2D version. If I'm somewhere over here and I want to, or over here and I want to walk down, like it's pretty smooth this way. But if I'm there at the top, maybe it curves so much that I can take a really big step. I kind of walk over all of the minima locally, and then some other kind of the loss space. Anyways, in general, this is what you want to do. This is gradient descent. This is gradient descent. But so meaning that we update the weights by walking. We think of our learning rate as a positive parameter. This is our gradient, and the negative sign is the opposite direction of the gradient. And we're updating the weights by just subtracting this from our current values of the weights to get the next set of values of the weights, right? And we just do this over and over and over again until we hopefully converge to something. And there's a lot of work that goes into getting this to work right, but in general, this is like the basic setup. There's some problems here. One is we usually have in deep learning, we usually need, because we have so many parameters, we usually need a lot of data to learn something that generalizes well. And so computing this full loss over the whole data set is really expensive. Right? Like if doing this over millions of images, every single time you're going to do an iteration, this will never converge. Converge eventually, but you might be 80 years old or something, right? It just is not the right thing to do. So we make yet another kind of approximation here in this wild world, and we do what's called stochastic gradient descent. And stochastic gradient descent is basically just it's gradient descent, but we estimate the gradient, the full gradient over all the data, by just using some subset of the data, right? So this is now another estimate, being made here. The first estimate is simply that, that the data set that we have estimates the distribution that we care about. But now now we're just taking a subsample of that and hoping that the gradient we compute with just that subsample of data. So instead of having 1 million images, now maybe you're going to have 100 images, or maybe you're going to have even less than that. But you will compute that gradient with just that. So the things that change is you do the sum over just the batch, or mini batch as it's called. And you're still doing an average, so the number of points you have is the size of the size of the number of points. And so now that's our approximation, our estimate of the gradient, and we use that, and that's why it's called stochastic, because there's like this random selection of the batch, the subset of your data that you're going to compute this. And every time you update the weights, you're gonna do basically another random sample. And there's a whole bunch of interesting practical approaches to how you do that, but that's the basic setup. And so that's what we do. So we have this totally non-convex surface. We're trying to find some reasonable local minima of. We have too much data, so we actually do stochastic gradient descent instead of gradient descent, and this actually works in the end. It's amazing. We actually find parameters, values of the parameters where our classifier, for instance, performs extremely well. Again, why it works, I think, is still pretty, explaining all the parts of why it works is a pretty good research problem still. That will require many, many, many years, probably more, of figuring this kind of thing out, but there's a lot that's been worked out. By the way, there's a lot of thinking that this estimation here acts as another kind of regularization to the problem. So regularization is going to pop up all over the place. It injects some additional noise that's actually beneficial for wondering about this really crazy loss surface. Questions so far? Yeah.
Yeah, I think stochastic gradient descent is done for every single example, but mini-batch is different from the stochastic gradient descent. Or am I missing something? Because from what I know, stochastic gradient descent is done for every single training example, and mini-batch is a set of training examples. Mini-batch is basically a trade-off between stochastic and the full loss of data. So,
I'm not really sure what you're getting at. You're saying that there's a strict definition that stochastic is one example.
Yes.
I don't think that's the case, but I don't know. Maybe it is. I'm pretty sure it's not. But look it up. But yeah, that batch could have from 1 to n-1, where n is the size of the data set, and it would be stochastic gradient descent.
So it seems to me that the loss function is non-convex.
It's extremely non-convex. Yep.
So what is a common practice to make it convex, or
you don't make it convex? No.
You just have to deal with it.
No, you don't make it convex. We'll learn some smart ways of randomly initializing the parameters, but it's going to put you in some part of the space here, and then you're just going to perform gradient descent, and it's going to find one of those local minima. It turns out that for most of the variants of the stochastic gradient descent scheme that we use, and the initializations that we use, that we seem to always find a local, not the same local minimum, but a local minimum that is equivalent in terms of the performance you get on the task to all the other ones that you would find. It's a really interesting phenomenon.
So how do we initialize W? Isn't it some random number that's close to 0?
Yeah, we'll talk more about initialization. That's coming up.
Does it matter if you initialize it 3 or 4 times and then run them all and see where the ball's going to roll to?
No, these days there's enough known where initialization is still random, but it's actually there's not a whole lot of difficult thinking that needs to go into it. Now, there used to be a real need for this when the architectures were really simple in terms of there weren't normalization layers and things like that. But now there's a lot of tricks to the architectures that sort of reduce the dependence on getting a really excellent random initialization. But we'll talk more about that as we go. All right. So backpropagation. So we've got all the tools. Now we just need an algorithm for basically computing these gradients fast and efficiently. That's it. And backpropagation, boy, I wish I would have the paper on me. I don't have it. 1980 something. Papers written. that describes the backpropagation algorithm. People started using it, but of course they didn't have all the fancy compute that in the 80s that we have now. And so while like neural networks were trained using backpropagation back then, like they couldn't train very deep networks at the time. And also for all the crazy things that we'll talk about as we go here about just how hard it is without certain like neural network architectural decisions to get things to start off in the right way. But nevertheless, this is described, and as was pointed out earlier, it's really just application of the chain rule in calculus like over and over and over and over and over and over again. So we talked last time about computation graphs, right? You think about all the operations you're doing from the inputs to the outputs as like a graph of like kind of a flow of the data from input through output and all the transformations that are being made through different operations, whether they're simple operations like arithmetic, addition, multiplication, are far more complex ones. Maybe like softmax transformation, like as a whole, is a kind of more complex transformation. But nevertheless, you can think of these as like you think of this all as a graph, and where the edges represent the data as it's flowing from input to output. So for us, it's going to be think of images as input, and then we want to compute the loss as the output. So there's all this computation that happens along the way. And these graphs become really important because they're like the backbone in which we do the backpropagation algorithm. And you'll often hear talk about like forward and backward passes when doing like the gradient gradient descent. So the forward pass is exactly as it sounds. Input pushed forward to the network to the output, the loss. The backward pass is what we're going to talk about today, how we propagate gradient signal from the loss all the way back to, when you think about it, this is like really important, right? The loss is the signal that says how poorly we're doing, right? Like where things are not currently right in terms of the task we're trying to do. And so we want to start with the loss and propagate that signal through the entire network, through all of the weights. Like we're gonna have networks that are layers and layers and layers of these like linear transformations deep with nonlinear activations, as they're often called, but these nonlinear transformations in between. So we need to be able to pass that signal all the way through at each layer, like getting the correct gradient to use to update those weights at that layer. So this is actually fairly simple. Thank goodness that it turned out this way. The way you think about this is that you're going to be computing gradients everywhere, right? So this says z, like you think of f as like taking x and y and outputting z, right? So we're just, the inputs to f are x and y. This could have said f as well, but you can see z as the output there. But local gradients just mean these partial derivatives. So if we just look at any node in the graph, any transformation f, we can compute local gradients with respect to the inputs. Did you have any problem with this, Sheila? Statically turning off your monitor? No. I keep doing it. Anyways, and then from who knows how far down from this transformation, somewhere down the line there's a loss that's being computed. And what we need to know, what backpropagation does, is starts from the loss and just continues to like accumulate this gradient information until we get to like say this transformation. And at this point we know what the partial derivative of our loss is with respect to the output of f. Okay? So we have that information coming from from downstream that way. And then we have these local gradients. And we can combine that information, information to pass the derivative of the loss with respect to either x or y here to the nodes, to the transformations previous. And the way that we do that is through the chain rule. So what is the derivative of this loss with respect to x? Well, we have this variable in between that mediates this z. So by the chain, so if you think of this as a composition, right? L of z of x, so to speak. So this partial derivative is just passed through z here, and the way that the chain rule works is just we get the product of these two partial derivatives. That's really awesome. Like, if it was something much more complicated than the product, we probably wouldn't be using backpropagation, or at least we would have, we'd have hardware that could do that other operation. Yeah, it's pretty simple. So it's very simple to do this algorithm. Like at every node, once you get that downstream derivative, to pass it back again further and further upstream, you just compute local gradients and multiply it with them. And then it just keeps going and going and going. And same thing for y, we just now taking partial derivatives with respect to y. So both of these use partial L, partial z, but they just multiply with their respective local gradients. And this is like the heart of backpropagation. There's really, in the end, there's really nothing more to it than this. Yeah.
So for a library like JAX, like you're mentioning, you can define your own loss function, and it'll analytically calculate the loss.
Not analytically, automatic.
Oh, automatically.
Yeah.
Calculate the loss here.
Yep, that's exactly right. But this is not just JAX. This is PyTorch, TensorFlow, all these other things. JAX allows you to have far more wild loss functions as a result of the way it treats differentiation as like a first-class operation. But yeah, exactly. And that's like one of the major. It's like one of the major contributions that these things make. You might have heard of Theano. Anybody heard of Theano? Theano was kind of like the first kind of really popularized like deep learning framework. There was also been around the same time like Caffe and a few others. But like Theano's like big contribution was it had a really great automatic differentiation idea. That's what people used it. Now, what else does like PyTorch and TensorFlow? What else do they add? They add like libraries and things that implement all of the building blocks for all of the stuff you want to build, right? Like if you want to build, 1,000-layer, residual network, it's going to have all the blocks, the building blocks for building those kinds of things up, and a very simple API in Python for creating those. But once you have that whole graph created, then that propagation, automatic differentiation just kind of takes over, and you don't think about those details. It's implemented for you. Super nice. Okay, so this keeps being passed back. So let's go through an example. I can't remember. I think you did this at the end of a simple one of these at the end of last time. But if not, doesn't matter. We're going to do another example here. So here is a computation graph for that function f up there. So it's a function of the parameters w and the input x. Turns out, if you look at this, w is a vector of 3 numbers, w0, w1, w2. And then x is just a vector of 2 numbers, x0 and x1. This w2 acts as like a kind of bias term, in that operation up there. So, but it's just, it's 1 over 1 plus e to the minus that sum. Okay? And these are the values of the w and x here. Just listen along here. And then what we did was a forward pass. And green is the forward pass, right? So we forward through the operations here. So like, it's not always unique how you would kind of split these up into operations, but here's a way of doing it, right? So you need to multiply w0 and x0 together, and if 1 is 2 and 1 is minus 1, and you multiply them, you get minus 2. That's what you see in the output from that node there. and then kind of so forth, right? W1 times x1, it's minus 3 minus 2, you get 6. And this W2, it's going to be added to the sum of these things over here, right? So the next operation is just to add these two, and you get a 4. Then we're going to add that and that, we're going to get a 1. And then we're going to multiply that by minus 1, that will give us the exponent, right? So now we have minus 1, and we exponentiate, right? So like, this is like a fairly complex operation, but you know, we just represent it as just the exponentiating with the natural base. So that gives us approximately 0.37. We're going to add a 1, and then we're going to take the reciprocal of that. That's going to give us the output of our function, right? And you can just, the first time you can think of it as like the loss. So it's just, this is just like, you know, it's a not so simple computation graph. So now we're going to do backpropagation with this, okay? So we have our forecast. We now want to backpropagate the signal from the output of that function back through the parameters here. Okay, so how does this go? Well, a couple things. One is when setting up this algorithm, so green remembers forecast. We're going to use red as backwards pass, and if you're green, red, colorblind, I apologize. But green, so forward passes on top, backward passes on the bottom. What do we have here? We're going to start with some value of the loss, or of this, like an initial derivative, so to speak. It's going to be 1 because multiplying by 1 doesn't change anything. And then we're going to start kind of backpropagating that through. So what else do we need here? Well, we need to know, we need to know the derivatives and everything to do. We need to know all the partial derivatives as we go through. So here's all the derivatives of things that we can do. And you probably already knew that, but here they are again. Okay, so the first thing we need to do is we need to take a partial derivative of this function right here with respect to its input, which it's only got one input. So it's going to be just with respect to this input. Here's the value, but remember it's a variable. We're going to take that and we're going to apply. We're going to calculate what that derivative is at the point x. Okay, so it's 1 over x. So we look up in our table here. We've got a derivative of that. That's minus 1 over x squared. Right? So there you go. And then we are going to input the value of x at this node. The values of the variables are just 1. So that's 1.37. We put that into the derivative here. So that's our partial of this operation with respect to its one variable. And we evaluated at the value of that variable from the forward pass. And then we're going to multiply it by basically like the upstream derivative at this point, which you can think of as like, it's f, like if you think about it like as the loss, this is like partial L, or partial F, partial L. Right? So that's what, it's a 1. It's like a starting derivative. And we're going to multiply it. So we do all that calculation, and what we have is that our partial of f with respect to this operation now at these values is minus 0.53. Okay? Questions about that? If you have a question right now, it's best to ask because we're going to keep doing this over and over again. It's just going to get not more complicated, but maybe more confusing if you don't know what's going on in the first step.
So do you use the 0.73 anywhere? Or is
No, because that's the output, right? So like that's the output of the loss at that point, or the output of this function. So like if there was one more operation to do after that, then you would use it. But it's like, yeah, it's just like the final variable. So when we're doing these things, when we're taking these partials, we evaluate them at the values of the variables coming into the node. Yeah.
So are we always going to have that 1 unit every
Yeah.
time we start?
Think of that again as like partial f, partial f. Right? So like, I don't have names, but I don't have names for them. But like, this right here is partial f partial 1 over x, like whatever this thing is right here. Like call it, I don't know, y, if you don't have a y on here, but call it y. This is now like partial f partial y. But over here, like this is right here, but this was partial f partial f. So that's just a 1, right? It's just like the simplest thing is so it's always a 1. It's always a 1. I saw other hands. These are good questions. Okay. Okay, now we do the next step. So now, again, we've got our like partial f partial whatever this operation is. Now we're gonna keep back propagating, right? We're gonna go back upstream. Okay? So this is just an adding by a constant 1, and there's your derivative, right? It's just 1. So we're going to take that, before I put it up there, we're going to take that derivative, we're going to evaluate it at 0.37, but there's like nothing, this is a constant. And then we're going to multiply it by the downstream derivative, right? Which is minus 0.53. So what should it be?
Minus 0.53.
That's always like scary for me. Because I didn't like study these very hard beforehand. It's got to work out that way. But yeah, minus 0.53.
Yeah, in the earlier slide, it said that we were taking the derivative of the loss with respect to the output, and here it looks like we're making the derivative of the output with respect to the input. And I guess I'm wondering if I'm reading.
Well, so what we're accumulating along the way, so it's hard because like you just can't have it. I mean, you can put like value, you can put variables in all this, right? But like think of this as like, I don't know. What do we use here? Like forgive me, I don't use. P, Q, R, S, I don't know. Like just call it like that. It's like what these are. Like the output is like this. So this was, I said this was S, this is really F, but this is the partial of, what this number is here is the partial of F, or just think of it as a loss, so you can maybe replace it with L. This is the partial of L with itself. This is now the partial of L with respect to, I call this R, I think, right? Or I guess, what do I call this? Yeah. Doesn't matter if I can't remember you up there. So it's partial of F or L with respect to that, and it's partial of F or L with respect to I guess I called that Q, and so forth. So like we're accumulating that gradient going backwards, right? So it's like it's the partial of whatever our output is at this step of the algorithm, and we're just going to keep pushing it back until we get that all the way back to the inputs. Does that answer your question at all?
Yeah, I guess my question is like 0.73, is that the loss of this function or is it the output of this function?
It's the output. It's the output because this is just a function.
Right.
We don't actually have a loss here.
Okay.
But you can also just think that maybe this f is the loss. Like f is itself a loss function.
Okay.
Even though it's not. It's just something that is a little bit more complicated than what we've seen so far. It helps to kind of.
But regardless of the function, backpropagation.
Yeah, exactly. Regardless of the function. Yeah, exactly. Okay, good questions. Other questions? We just keep doing this, okay? Yep, the exponential function here, e to the x, its derivative is e to the x. So we're going to do what? We're going to take its derivative, the local derivative, which is e to the x. We're going to evaluate that at negative 1 here. So it's going to give us an e to the minus 1. And then we're going to multiply that by the downstream gradient. Minus 0.53. So that's going to give us some, tricky number of some kind. And, oh, look. There you go. Roughly minus 0.2. Okay? So we're just going to keep doing this. Now what happens when so this next one, this is just multiplying by minus 1. So you know, if you multiply by a constant, take the derivative, you just get that constant. So the derivative is derivative here is minus 1. It doesn't depend on x, so it's just minus 1. We're going to multiply that by minus 0.2, and we get 0.2. Okay? And now we get to maybe the first sort of interesting thing. We've got two branches kind of coming into here. So what do we do? What do you think we do?
You do the gradient for each one.
Yeah. We're just going to work our way back and we're just going to do this. We're just going to do it for each branch. Okay? And again, these are just because of the nice properties of like differentiation, being like a nice linear operation. So we're going to go through both branches. Our downstream gradient right now is 0.2, and we're adding these two numbers together. This, you know, like the output of all this graph right here, and then W2. So there's going to be a partial with respect to this output here, and a partial with respect to W2. And then we're going to multiply that by 0.2. All right? So this is a sum. So when you take the partial, you're just going to get the other number plus 1. Right? And so you, let's see. Oh, yeah, look. Exciting. So we had let's see, what am I saying here? I think I lost my stuff. Yeah, local gradients. So this local gradient right here, this number coming into here, we would take the derivative of, so I don't know, call this like, I don't know, call it B for right now. So the partial of this operation with respect to B would be the so it's constant with respect to, what am I trying to say here? I wish I tried something else here. But when I take the derivative with respect, so like this is, think of this as B plus W2. So I take the derivative with respect to B, I have a 1 here, and then this is a constant, so it's a 0, right? So I have a 1 plus 0 is 1. And that's why this is, showing 1 right there. And then I backpropagate the 0.2. So I have a 1 times 0.2, I give a 0.2. When I go the other direction, then the same thing happens, right? When I take the partial with respect to W2, I get a 1 for the W2. And that was a constant with respect to W2, so that goes away, it's a 0. So it's a 1 again times 0.2. So now we've backpropagated this whole thing. So let's just stop here before we move on. What is this right here? This is the partial of what with respect to what?
Loss with respect to W.
Yeah, the partial of like the full function, or you call it the loss, f, with respect to W2. So I have, so if this was a loss, I have the gradient of my full loss function with respect to W2. I now have the gradient I need to update W2, my weight. Okay? My other weights are here, W1 and W0, or W0. So I got to keep going to just get those values. So and we have another sum, so that's going to give us, we're going to keep propagating back that 0.2. And then I have multiplication here. So when I do this, when I do the part that says, W0 times X0. So when I take the partial with respect to X0, I get W0. When I take the partial with respect to W0, I get X0, right? Because they're multiplied together. And whatever the value is there. So, like for instance, the partial of this operation with respect to W0 is X0. X0 is minus 1. Minus 1 times 0.2 is minus 0.2. And then the other way around, we have, every year I say I'm going to fix that. And it's not fixed. Never fix it. It's so bad. So the other way around, I have partial with respect to X0. That gives me W2. It should be 2 times 0.2 is 0.4. But for some reason on this slide it says 0.39. So numerical error. I always say I'm going to fix it. I never fix it. But it's fixed right there. So there you go. 0.2 times 2 is 0.4. So now we backpropagated to, so now we have partial f with respect to w naught. So now we know what the gradient is for that value. We could use that to update it, and then we can do that as well. Okay, so that's it. Like that's what backpropagation looks like. Of course, these computation graphs can get crazy wild, right? Like this is a pretty simple one, and we're gonna have we're gonna have many layers, probably hundreds of layers at times. That's going to represent, each one of them is going to represent maybe 3 or 4 transformations, because like usually a layer is going to have both like a linear operation with some sort of normalization, with possibly a kind of like regularization, like dropout, and possibly some other, and then a nonlinear transformation. So you're going to have like each one of those is going to represent some other operation, and you're going to have to backpropagate through every single one of those all the way up, through the end. And then, I mean, we haven't really spent a lot of time on this yet, but you'll see each of those layers will have its own parameters. So as I'm backpropagating through, I'm actually like figuring out what the partial derivative of the loss is with respect to the parameters in a layer that's like close to the loss. And so I'll have those values for updating the gradient. Then as I move back and back and back, there's I'm going to eventually get, like we had here at the very beginning, I'm going to eventually figure out the gradient with respect to all of the parameters. Yeah?
Can you please explain how the local gradient is proved in this case?
The local gradient is 2. For x naught, yeah. So it's a product, right? W naught times x naught. And I take the partial with respect to x naught. So that leaves me with w naught, and the value of w naught is 2. The green value. Yeah, I can't reach that high. You see it at the very top there? Like that's what that's what I'm left with, right? There's never like good luck in this class. I don't know. It's just it's w naught times x naught. Or just w times x. I take the partial with respect to x, I'm left with w. What's the value of w of this part of the operation? It's 2. So that's what the partial of the local gradient with respect to x is. Doesn't seem like it's jiving. Does that make sense? Oh, okay, good, cool.
Yeah. Is it possible to have an operation that's not differentiable?
Mm-hmm.
Yeah. So how does the computation of graph is going to work with that thing?
Yeah. So oftentimes the name that this is given, like this kind of like approach to programming, like if I want to learn how to classify cats in natural scenes, this is sometimes called differentiable programming. The point being is that you need to be able to take derivatives of things. So like we make sure that we have differentiable operations throughout all of our transformations. Sometimes there will be operations where it won't be differentiable everywhere, but the points where it's not differentiable will be like discrete points. They're points that you would never in practice find, so it doesn't matter. And if you did, there's usually like a way of picking what the gradient should be there. But the point in general is that the transformations that you're working with are differentiable. They're differentiable usually almost everywhere, is the way you think about that. And you can even relax that some more. Like that's what Jack's allows you to do, is kind of go to things that aren't typically thought of as being differentiable. But in general, just the basic framework is just we're going to use differentiable transformations. So we can do this.
So these values that we're getting from backpropagation, what are they actually used for?
Yeah, right. So remember how way back when, what was that? Remember we wrote down this, and we said we're gonna update our weights by computing the gradient of the loss with respect to the weights. Well, that's what we're doing. Is we're computing the gradient of the loss with respect to the weights. Those partial derivatives are what that's the gradient. That's like for each weight, that's telling us, the rate of change of that parameter locally at the current value of the parameters.
So that's like the value that points us down towards.
So, well, it points us up, and then we multiply by -1, it points us down. And so we're calculating this thing. We multiply by some learning rate, meaning we don't necessarily take like one whole step in that direction. We might take a small step. We might take a huge step too. It kind of depends. But how far do we move in that direction is determined by this parameter. And there's the minus sign for going down the gradient. And so we're just adding that to the current value of weights. That's what t is, like iteration t. And so now when we go to iteration t plus 1, the weights are this updated value. That's what this whole thing's for. Great question. Yeah.
In practice, we usually calculate the backpropagation for the x variables since we're not really updating them.
You're right. Yeah, like you don't need those. Like at the end, you might need like intermediate ones. Like you certainly need the intermediate ones. Well, I guess not always, but you typically will need the intermediate one because you'll have weights that like were inputs to that. But you're right. Like in this picture here, you don't need. Yeah, you wouldn't need to calculate this or that because it's an input on a train. However, there are things that people do to like say, like let's use the loss to like create an image, to create some sort of input that like is like a characteristic image for a class. And so you start with like a random image, and then you do gradient ascent on like the loss from a particular class. Like you're trying to adjust the input given the parameter values. You're trying to increase the input. Right? You're trying to change the input so that it increases like the value of the score, not the loss of the score. And so like you kind of reverse this whole process and forget about the weights, think of them as fixed, and just work with like the pixel values of like not x1. We'll actually do some of that in this class, but it's like a.
Is that how you get those like generated images?
Yeah.
What the computational horses?
Yep, that's right. That's exactly how you do it. Yeah. Well, that's one of the like standard. I suppose it's probably. Okay, I'm good on time. All right, keep going here. Please help if you have questions. Okay, so yeah, this slide just to say we broke down this like the computation of f in a certain way, but of course, like all of this right here was about computing the exponent in e to the exponent of e in that denominator, or at least e to the minus whatever, e to the minus x. It was all about computing that input. And then from that point on, it was like another function that we call the sigmoid function, 1 over 1 plus e to the minus x, right? And so all of this operation right here represents like a single operation, that one right there. And we could have, if we know how to compute the derivative of that thing, which turns out has a very simple derivative. The derivative of the sigmoid function, sigmoid, is just sigmoid, the sigma times 1 minus sigma. So like the function times 1 minus itself. And you could think of it like that, and then you can maybe skip over this whole thing and just do that. This is a lot of like the kinds of things automatic differentiation does, right? It's like, it knows these formulas, and takes care of that for you. But yeah, you could skip through and just go directly, say, to this in that way. If you see it, since this is the derivative, our value of x is 1. When we input that into our sigmoid, we're going to get like 1 minus whatever that value is times that value times the upstream gradient, and that's going to be 0.2 in this case. So typically these are not unique. It's just you just have to be able to do backpropagation. You need to be able to compute the derivative of every single one of the units. Right. Okay, so there's a couple of like patterns here. I suppose like it's interesting to notice. So when we were adding things together, the way that typically works, like what happens at an addition node is just that we take whatever this downstream gradient is and then just move it upstream. Right? If we don't change it, we just move it upstream. So we saw that, we did that computation. So what about this max right here? What is max doing? Say again?
A max function just output the largest.
Yeah, that was the largest one, which means it's making the output constant with respect to the smaller one. So we get a 0 for the smaller value in the max, and we just take whatever this gradient is, and because this is just like a linear function, derivative times is 1 with respect to this larger parameter, then we just have 1 times that until we get 2 again. So what's the max gate? Well, just you think it was maybe just routing it to the larger the values. And if it was a min, you'd be routing it to the smaller one. Yeah.
What happens if Z and W are equal?
Right. So then this is one of those. This is one of those times when you say, I don't know. No. You make a decision at that point of like what you'd like to do. So in practice, it never happens. Like if you randomly initialize things and your data is more or less, like has like a kind of random local structure or something like that, then like these kind of things never happen in practice. But like you typically will implement something. So typically what people do is to distribute it to both, or distribute half to both, or you don't do 0 to both because you wouldn't get any propagation of the signal. But you just make a decision.
Or you pick like the lowest index or something? That would
You
be all of them?
could roll the dice and pick one. As long as you distribute it. The important part is that this in practice has never happened. Because it's a probabilistically it's a set of measures 0. Like in terms of like randomly sampling from the value. So in practice you never see it. But you can pick something reasonable. It's the same thing with like any so like think about the hinge function that we have, right? The function is technically not differentiable at the point of where it hinges, right? So like whatever that value is. So what do you do there? You can pick it to have this derivative of 0, you can pick it to have this derivative of 1, you can pick it to have something else entirely. Honestly, it doesn't really matter. The point is that you're never going to see it. What about multiplication? What does multiplication do? Come up with these like really clever names. Gradient distributor, gradient router. What kind of clever name are you going to come up with this one? This isn't that good name, I think. Gradient switcher, yeah. So there's a multiplication that happens, right? So you take the other, when you're going up to this branch, you take the other value, multiply it, and that's what you get that value, and then vice versa. So for some of these simpler operations, it's like pretty. There's there's simple rules for that combination. Okay. Also, just following the rules of calculus of differentiation. If we had like 2 different branches coming in here, so we dealt with like the other case where there was like 2 branches coming in on the forward pass, but now if there's like 2 branches going out on the forward pass, you might think, well, what do I do here? But it's kind of nice, right? Like there's just contribute. Like remember what a gradient is? A gradient's like how much is this changing? Well, whatever's happening over here is changing it by a certain rate. Whatever's happening here is changing by a certain rate, and those rates just add together to give you like the overall rate from both. And this is going to happen quite a bit. Like we talked as if like there's only one loss function, but there could be many loss functions. Each one corresponding to some task or to something you're trying to learn, build into the network. And so the good news is that those just add. So you just add the contributions from both branches there. So that's nice. Like, everything's nice about this. Calculus just turned out nice for this kind of thing. You can do this in vectorized format as well, meaning that, like, instead of thinking of this as just like these are scalar values, everything as scalars, you can think of, like the x's and the y's and such as vector input, as is often the case like for a full layer or something like that. You might have all the weights from that layer, take the partial with respect to the whole thing. What happens in that case? Well, instead of having scalars, you might have, if this value is a scalar and this is a vector, then you have a gradient, right? You have a vector of partial derivative. But if this is a vector and this is a vector, then you actually have what's called a Jacobian or a matrix of partial derivatives. And the nice thing here is it's just like all matrices and these kind of things are like all of linear algebra is something like it's just like a method of keeping track of all these values and putting them in nice places so that the operations make sense. And that's what's happening here as well. Like, what does the matrix look like? Well, it just looks like it's just in the right shape so that when you do the products, everything kind of works out. Like all the right things are multiplying in the right places, all those dot patterns. But that's what you would get. It's just notation. It can get pretty hairy when you think about it. So let's say that you had, there's an older network called BGG that has an output has a layer that people would use for like representation of the image that has 4,096 features, or it's a dimension 4,096. And let's say that you were going to apply a max to that, element-wise, and so the output is again 4,096. So if I now compute the partial derivative of the output with respect to the input, what do I have? I got a matrix of what size?
4,096.
Yep, 4096 by 4096. 4096 by 4096. It's pretty big. That's a lot of floats, right? And it gets even worse, right? Because I need to do this for all of the values in my batch, which might be on the order of 100 or something like that. So I would typically have this gradient that's got 490,600 by 409,600 by 409,600. That size matrix. So like these kind of operations can get really big, really fast, even for very, very simple kinds of operations. And so, making these efficient is also part of what these libraries do for you.
Can you please illustrate how it is 4096 cross 4096 and not 4096 cross 1? Because it is basically an element-wise max function out there, so you just have one out.
Well, it's the output. For each of the inputs, there's an output. So it's your output with respect to your input. So it's
basically one input that is replacing one output out there, and so for each
right.
input,
So
it's a one-on-one mapping.
I think what you're pointing out is that it's like a sparse matrix. Like there's a lot of zeros in this.
No, it is a 4096 cross 1 matrix probably because each input is just influencing one output, and there is just a one-to-one mapping basically between the input and the output because it's a max function.
Right. So like in this very, very simple case, these arrows, like this arrow right here is only influenced by this arrow right here. Right. So you're right about that. So the full Jacobian is sparse. It's actually diagonal. Right? That's actually the next question. You kind of jump ahead. It's diagonal here, only because this is such a simple operation. Right? Max is just a simple operation. When you say this was now like multiplying by a matrix or something like that, then it wouldn't be sparse like that. But you're right. In this case, it is sparse, but still the Jacobian is 4096 by 4096. It's just sparse. And so again, like these libraries, they would never just kind of stupidly represent this matrix as like having all these zeros in it, right? If they're going to do these vectorized operations, so they would know better how to make these efficient. Like again, that's the point of like one of the things these libraries do for you is that somebody's written some efficient code for dealing with these kinds of like in theory, large outputs. Yeah, that's just kind of a simple one. So yeah, it's diagonal. You're right. But you can do backpropagation. I'm not going to spend a lot of time here because you can do backpropagation in the vectorized format as well. So you can have your inputs. So like in this, if now what we have is just this like simple the square of the norm of the vector wx, which just kind of looks like that for having n inputs, and then it would be two inputs. And we'd have a w that would be in matrix format like this. We have an x that would be in vector format like this. We have a matrix vector operation. That's what that first node would be, and then we would apply the L2 norm, the square of that anyways. And so you can do this forward pass, and then you can do the backward pass. You just have to be able to do like calculus with matrices and vectors, which again it's just bookkeeping. So it's just there's like rules around it that you can learn. And for like linear stuff like these, like just w times f is actually very simple. It's what you expect. But it has its own kind of rules for the calculus. And you would just you do exactly what you need to do. You calculate the so this operation is a square, squaring the input. So the partials just are 2 times this. So your full gradient is just 2 times the input, and so that times the downstream gradient of 1 just gives you again twice what the input was. And you just keep doing this. Like there's nothing different here. It's just backpropagation. It's maybe like also a little more succinct, but it could also be wasteful in some of the operations. I'm not going to spend time. But you can calculate all these things. Okay, there you go. Got all your weights. Got your partials with respect to those weights, and now you can do gradient update. A lot of your homework is like set up like this, to where you're going to compute a forward pass and a backward pass, and keep track of all the things that you need to for each of the operations, so that you can like implement your own backpropagation. And let's see. Yeah, the point is that you're going to have to like keep track of in the forward pass. So for the backward pass, you're going to have to sometimes have access to the values that you computed in the forward pass, as we've seen many times, right, in these operations. And so, like in Python, some simple kind of pseudocode here. If the operation is just x times y, you keep those values around. Your partial derivative with respect to x is just the other variable times the downstream gradient, which is an input to the backward pass, and vice versa, and then you return those gradients. So this is a pretty typical API for thinking about like how to implement these things, and you'll do that in a moment. But just know that after you've done this, like basically this is like the whole point of these libraries, like so you don't have to do all that low level kind of like calculations. There's just all kinds of layers. They end up being like Python classes, which have all this information already built into them. You just there's an API for like putting them together as like a computation graph. PyTorch actually does this. Doesn't have a static graph, it has a dynamic graph, so it actually builds the graph as you compute the forward pass, which makes it sort of easier to manipulate and maybe harder to reason about at times. But the point is that there's all kinds of layers. Like you click into one of these, you're going to find all the convolutional layers, and all of tooling and padding, and all of these like different kinds of activations and normalizations and recurrent layers and transformer layers and all these other things. And you're just going to have all these loss functions and things like that. And you're just going to be able to go in there and put those all together, and just know that in the background, all this kind of crazy backpropagation, all of that is built in and just will be done automatically for you in a very efficient way. So that's awesome. And this is true for PyTorch, this is for TensorFlow, this is JAX as it is for the NextNet and all the other things that are out there. Right, so, again, for your assignment, you're going to be doing this. You're going to be computing the forward and backward passes, and need to be keeping track of those derivatives, and being able to pass those back so that you kind of link these together. Information for forward pass, computing losses, taking derivatives with respect to that loss, and passing that backwards. So you get to have some practice. Anybody already done this already? Yeah, I remember you told me it took you a long time. It's going to take all of you a long time, so get started. I think I told you that maybe 5 times today. So do get started. It's sort of annoying, but that satisfaction when you get the right answer, like, hey, I did it, and never have to do it again. I'm just going to use PyTorch for that. You're going to end up contributing to the PyTorch project and all that.
You kind of named a lot of variables differently. Is that?
Yeah, just because these get stale. Don't worry about it. If you got the right answer, you got the right answer. Okay. So just review. Neural networks are going to be very large. There's going to be many transformations. It's going to be impossible to write down the gradient formula for all the parameters by hand. We're never going to do that. It just doesn't make any sense. So how do we do that? How do we compute these gradients with respect to the parameters? We're going to use BackPropagation like we just went through, and we're going to be able to do this for any graph that's got differentiable transformations, and we're going to eventually be using code that takes care of all this kind of stuff and gives us very nice APIs for doing this, and you're going to have a lot of respect for the tools that you're going to use after you do homework like this. So that's it for today. I'll take questions now, and I'll also just be taking